So welcome to our ALPO webinar this afternoon, which is on demystifying wavelets. Appreciate everybody being here. I'd ask that you put yourself on mute so that if there's some background noise or something on your end, it's not disturbing the talk here. And at the end of the presentation, as usual, we'll have time to ask questions and to go back over anything that you would like to review. So with that, let me see if I can get my screen share going here. Right, good. All right. So is this visible to everybody? Is it coming through? Somebody just kind of tell me whether you're seeing it or not.
Yes.
All right, thanks, Greg. So here we are, demystifying wavelets, how we use wavelets to sharpen images. I'm giving, as I mentioned to Greg earlier, before we started here, I'm the one doing this presentation today. So I will throw out the disclaimer immediately that I am not a subject matter expert in this. It is the sort of thing where I wanted to just kind of gradually learn more about this process. Because basically the problem statement is, how do wavelets work? And for a lot of us, myself included, it was kind of like, who cares? It just works. And especially if you're going to get into what I perceived as potentially heavy math. I'm not necessarily a math phobe, but I'm not a math file. So I was kind of like, well, I'm busy, it works. Who cares how it does what it does? But actually, it is kind of good to get a little bit of an understanding of what's happening, when we're using these wavelets. And you can see online, places like Cloudy Nights, occasionally a discussion will crop up in terms like this, for example, RegiStax wavelets, is it science or magic? So for a lot of us, it has kind of seemed like black magic. It just works. So, but gaining some insight as to how it works can really be helpful to you in the end. And it's not black magic. It is science. It is math underneath the hood that is creating this and allowing this to work. So, let's start with what is a wavelet. So most of us are familiar with the sinus wave. Back in high school in physics, or even math, you had the discussion of what a sinus wave was. An infinite, perfectly smooth oscillation, okay, with no localization. So it was not, a snapshot at a particular point in time. By contrast, a wavelet is going to have a start, a middle, and an end. So it is localized. A wavelet is kind of like a real world signal that exhibits slowly changing trends, and it can have spikes in it, like here, which we can term transients, that crop up along the line. So you have a line going along, and all of a sudden, whoop, you have some sort of a change in it. So a good analogy that I ran across when I was doing my research on this is that you could consider a sinus wave kind of like a flute player, where they're playing one or two notes alternately back and forth, back and forth. Whereas a wavelet is more analogous to like a drum beat. You hit the drum with a certain intensity and a certain pitch, and it's there just for that moment in time. So basically, the heart of all of our image magic is that it is a digital image that we are working with. So you can imagine that if we were to examine a row of pixels across our image, so we take a slice, and I'm running from left to right here across, we could take that information, in other words, the value for each pixel. So each pixel could be 000 for perfectly black, or 255, 255, 255 for a perfectly white pixel, and anything in between. So if we were to kind of take a reading across this image here where that line lies, we would basically get like a wavelet that would show us, the information along that particular line. So now think about defining a wavelet. So you go ahead and you create a certain wavelet, and then you start sliding your wavelet across the wavelet that was produced as we went across this line. And as we're doing that at each pixel, we kind of ask, does the image look like this little wiggle right here? So in other words, it's kind of like having a stencil and pushing it across your readout. Are there areas where you're matching up? And this would kind of be a fuzzy matching. Of course, you're not going to have, I create some sort of a small wavelet to represent changing a boundary. So let's say I create a wavelet that kind of somewhat might mimic where we go from the limb. So you're going to look for fuzzy matching. It's like, okay, it's not a perfect match, but maybe it's a 90% match or an 80% match or a 25% match. So that's kind of at the heart of what's going on here, is that you define a wavelet. You then kind of apply it across the data from your image, and you assign values for how well does this created wavelet that I have match up with this particular part of the image. So, and then we could obviously define a set of these wavelets, not just one, and they can differ in amplitude or intensity, how strong the change is, and frequency, the speed, how quickly the change happens. Planets in general have got smooth gradients that are interrupted by sharp boundaries. So our wavelets are really going to be good for detecting where those boundaries lie in the image. So take a little detour for a moment here. Some applications that use wavelets, RegiStax was, I think, probably one of the first doing this. It is, I think, a testimony to this application that it is still in use. I know I personally still use it a lot. And it's going to be our example today for talking about wavelets. However, there are certainly other applications that are using wavelets. LuckyStack Worker in its interface, you can see that we have, for contrast, it has fine details, medium details, and large details. This is a little bit different, but the same sort of principles apply. So it's a little different than how RegiStax is doing it. But if you kind of grasp how the wavelets are working in RegiStax, it would translate over to a large extent for LuckyStack Worker too. And then there's also this WaveSharp, which I believe is the successor to RegiStax. It is similar in that in RegiStax, we have the ability to apply a sharpening quotient and a denoise value. The same sort of thing is present here in WaveSharp. One of the differences, though, is that we only have 3 as opposed to RegiStax having 6. So as I said, in RegiStax, you're going to have 6 sliders, each with a particular wavelet that's going to match against the image and produce a layer. So layer 1, this is where you're going to have tiny, fast changes. So it's not a very strong change, and it happens relatively quickly. So it's like as you're going across within 1 or 2 pixels, all of a sudden you have this slight change in the image. So it's not very strong, and it's going to occur quickly after only a couple of pixels. The opposite of that, if we go all the way down, is layer 6, which is for basically big or strong, slow changes. So a strong change that happens over a dozen or maybe a couple of dozen pixels. So it takes time for that change to occur. The layers in RegiStax are basically a progression from those small changes in intensity that happen quickly down to the large changes in intensity that take time to occur. And an example of that would potentially be the limb of a planet. So when I first came across that, I was like, well, how is that to me when I'm at just my gut? The limb here, well, gee, that looks like, yeah, it's a very strong change, but it looks like it happens quickly. So, intuitively, it seems to me to be happening fast. So, why is that ending up at the level 6 slider? But, if you think about it, and if you zoom in on that unsharpened image, you're going to see that the change is indeed happening over dozens of pixels. So this really is a slow change, even though to your eyes initially and your gut, it might seem like it's a very abrupt change. So when you load your image, RegiStax is going to analyze and break the image into those 6 layers. As we've kind of mentioned, layer 1, very tiny detail. Layer 2, small detail. Layers 3 and 4, increasingly larger detail. That, again, is not super fast. It takes a little bit of time, maybe 4 to 8 pixels before the change occurs, all the way up to those very broad, slow brightness gradients that are in layers 5 and 6. So each layer contains basically a wavelet coefficient. And this is a measure of how much structure exists at that scale. So, like, for example, in level 1, it's going to take your image, and at each pixel, it's going to assign a coefficient for how strong does that particular pixel seem to be involved with small, fast changes. And each layer, same sort of thing. It generates basically a copy of your image, and it assigns values to each pixel in terms of, okay, for my particular wavelet, how strongly am I matching at this particular point in the image? And so basically you can almost, like in Photoshop, you can almost imagine that we have 6 layers, from the tiniest, smallest, fastest changes to the largest, slowest changes. So in RegiStax, we have that little lever according to each of the levels. And if we move that slider, that basically is going to change the strength of the coefficient in that layer. So you're not changing the shape of the wavelet. That's holding the same. But a good way to potentially think of it is that your wavelets are like a set of paintbrushes. Slider 1 is a tiny paintbrush. Slider 6 is a very large brush. And so when I'm sliding that lever, that slider in RegiStax, as I move to the right, what I'm basically doing is I'm changing how much paint I'm going to apply with that brush. So more paint is going to be basically more sharpening. It's going to add contrast. So my wavelet is looking for a slight change. And we've got the coefficients at the various pixels. By sliding that lever, I am increasing the intensity. It's like I'm applying more paint to that particular area of the image on that particular layer. So let's talk a little bit about some of the layers here. Layer 1 is really rarely useful. Again, I keep saying it's small changes that happen quickly. So here's an unsharpened image of Jupiter with layer 1, and then here it is adjusted to a value of 40 with the slider. So what would be a common example of a small change that occurs over just a couple of pixels? So one of these small, quick changes. Well, basically, that's a wonderful definition for noise. And if we zoom in here at my setting of 40, you can say, yeah, I'm basically, my picture is becoming noisy because when I'm sliding that layer one lever, I am basically saying, hey, go ahead and increase the contrast for the noise in my picture. So clearly, layer one, there are some situations where it might be helpful, but in general, you're better off leaving it alone in RegiStax. Layer two is going to be a better choice if you're trying to sharpen some small, fine detail. But even then, you still need to be a little bit cautious that you're not going to be also turning up the noise level with this. Layer six also is going to require some caution at the opposite end. Again, these are large, slow changes in the image. So here's an unsharpened, and then layer six at a sharpening of 5. So, not too bad, beginning to improve here. And then at 40. Okay, so to me, I know I get these as the person who kind of is processing them for our gallery. And, you really, it's really over processing too much. You get to the point where you're applying too much paint to these features and you're kind of losing the natural appearance. So it's definitely still, I guess maybe 5 years in the future, AI will do all of this for us. But right now, it is still a bit of an art on your point, but you want to try to make sure that your art is not exceeding the science. You don't want your art to end up creating artifacts or things that are not really there by pushing things too far. And that can especially happen in layer six. Layer six is also capable of, and a reason why you have to use it with a very light touch, producing ringing and halos. So ringing, we tend to see this kind of like, I think people refer to it as like an orange peel effect or orange rind effect. And basically you get an outline of brightness around the edge here. And I would imagine with Venus too, like in infrared, layer six could be quite detrimental. So in those sort of situations, you really want to leave layer six alone. So again, main takeaway is layer one, you're going to be very, very careful with that because of the noise it will accentuate. And layer six, it can end up causing things like ringing and halos around your object. You're probably better off dropping back to layer 5 for some of the larger scale changes. So general guidelines, we're probably going to leave layers 1 and 6 alone or with very, very slight adjustment. Layer 2 is going to be able to bring out fine detail, but you should still be cautious regarding the side effects of also turning up the noise in your image. Layers 3 and 4, this is where, in general, the good stuff is. Changes like an edge or a border that are medium intensity and happen over 1 to 8 pixels. So especially for a lot of our images, layers 3 and 4 are going to be where we mainly want to kind of work with that slider and to try to find the happy spot. Again, layer 5 can help with highlighting shadings or gradients. So if there's a particular gradient that you want to try to pick up on, layer 5 can be helpful with that. So let's talk about coefficient boosting and the whys behind that. So there can be times when you have moved that slider as far to the right as you can go, but you feel, I really need some additional sharpening here. I'm not quite happy. I wish that I could go even further to the right. So an example of when this might occur would be if you're doing drizzling. Things that come to mind for me are like a small Mars image, or if I'm taking a UV Venus image, because a lot of times I don't use the Barlow for that. When you do drizzling, which is basically kind of like expanding, enlarging, your image, your stacked image, the signal is going to be spread over more pixels. So the fine scale coefficients are going to get weaker. And so That's why you might see, hey, I've gone as far over to the right as I can, but I'm still not, I know that there's better detail there. Another use case is if your seeing has been soft. Again, same sort of thing. Poor seeing is going to spread that detail out. So you might have a festoon that is probably actually about 3 pixels wide. If it gets smeared out because of the seeing, ends up becoming 6 pixels wide. And so that changes it. It makes that coefficient weaker. So, for that particular layer, you go to that pixel, the coefficient value on that pixel is going to be lower because of this. Undersampling is another example. Basically, undersampling is where you are cramming too much detail per pixel. So, for example, using a Schmidt-Cassegrain F10 without a Barlow, a lot of times you might end up doing undersampling. Or if you have a particularly small target, you might have undersampling. Another one is low contrast targets like Venus and UV or Saturn. On your low contrast targets, these wavelet coefficients are going to be small to begin with because you don't have these really big changes, things that you can see immediately. So that requires you to boost those coefficients just to kind of, get it above the signal, get that signal above the noise floor. And finally, maybe this is a little counterintuitive. If you do happen to get a run of really good data, you have a great signal to noise ratio. Well, you got a lot of wonderful data in there. And that means you can probably push those coefficients harder than you might on a night of average seeing because the noise isn't there. It's not going to explode on you. You're not going to have to manage it as much. And so that's going to allow you to bring out detail in the fine layers. So, by bumping up the coefficient, when you have one of those wonderful runs where you have a good signal noise ratio, this will allow you to really kind of get even more detail out of that wonderful data that you've captured. So how do you do it? So in RegiStax, in the Gaussian mode, okay, we have the sharpen input box. It might be helpful to think of this as like a gain setting, which is going to increase. So a value here of 0.300 would mean boost the coefficient on these pixels by 30%. Okay, a value of 1.0 means use full strength. Public service announcement, I have never seen where that works. That's overkill. But absolutely, changing it to maybe a 0.2 or a 2.5 or a 0.3 can be very helpful. And of course, we start off with, when you first load your image, it's going to start off with a value of 0.1, which means you're basically giving a little boost to that coefficient at each point in the pixel on that particular layer. So when RegiStax then goes and it reconstructs your image, so it merges those layers back together, those boosted coefficients are added back into the pixels, and that results, the higher the gain, the stronger that layer's contribution to the final image. So we can see here the contribution by layer 3 here is going to be 3 times that of layer 1. So I did not touch layer 1 at all. I did slightly touch layer 2, but layer 3 and 4, which again are like where the sweet spot is, where we really tend to be able to accentuate the features, those are going to be 3 times more pronounced when it recombines those layers into my final image. So in the Gaussian mode, we also have the Denoise input box. So when RegiStax decomposes your image into the wavelet layers, each pixel, as I've mentioned, gets a coefficient that represents how much structure exists at that scale. So for each pixel in the layer 1 layer, each pixel has a certain coefficient, and as to how much that particular area mimics or looks like a small fast change. So the denoise slider, or up down, actually not a slider, if the coefficient is smaller than the threshold that you set, it treats it as noise. So what this basically is doing is, by increasing this value here, because it starts off at 0, that is going to look at each coefficient, and it's going to create a floor. If the coefficient on your pixel is below that floor, it's going to drop that pixel in terms of doing any sort of enhancement, any sort of increase in it. It won't apply paint to that at all. So this is why, it's helpful in that it can help reduce, if you are using layer 1 or layer 2, you can use this noise setting here to get it to drop out the low coefficients, which are probably noise, and yet still hopefully hold on to the higher coefficients, which could probably reflect structure. So your denoise is deciding which coefficients survive and get paint applied to them. And the sharpen, okay, over here, is going to decide how strongly those surviving coefficients are boosted. Okay, the Denoise strategy, it kind of, and this is not going to be a shocker, it changes by layer. So layers 1 and 2, you're going to want to use more of the Denoise value because those are the layers that tend to be noise heavy. Layers 3 and 4, you might apply a little bit there. Those layers basically contain the good stuff. Layers 5 and 6, you're not going to have noise at those levels. And so you probably aren't going to do much, if any, denoising at the higher levels. So let's take a look at Jupiter, which is a high contrast object. Slider 2 is going to be helpful for the fine structures, but it's also going to have some noise. So we're going to want to do a little denoise. It's going to be very helpful for those thin festoons and small rifts. So, if you got like a really thin festoon here, slider 2 is going to be helpful in trying to bring that and accentuate that. Slider 3 is for fine detail, but really atmospheric structure like festoons, rifts, small ovals. So these kind of festoons through here, a small oval, it's slider 3 that'll help accentuate those. Slider 4, you're getting into the medium scale cloud structures like edges of the North Equatorial Band or the South Equatorial Band, larger rifts, BA and greater red spot structures. The edges of BA or great red spot. And then slider 5 is for the larger atmospheric structures, kind of like the broad shading transitions. It can help accentuate those, but again, very light touch on these higher sliders. So, belt shading, great red spot, interior shadings, brightness changes, large ovals and barges, they can be helped by your slider 5. Now let's take a look at a low contrast object. So slider 2, for example, ultraviolet Venus. So slider 2 in general is going to be one of your more useful sliders. So that's a little different than what we were seeing with Jupiter, where it was 3 and 4. And that is, these subtle streaks and wisps, these are fine contrast in the equatorial and fine contrast in the equatorial band. Basically, you're looking at things that are very subtle. And so you're going to need to boost them with slider 2 because they're small. And you're going to ask to also take care of the noise, to be careful that you're not accentuating the noise too much. Slider 3 is probably the second most useful. It provides the main ultraviolet cloud bands and large streaks across the mid-latitude. Slide 4 would be a very, very light touch, broad cloud belts and kind of hemisphere scale contrast. Slider 5, you pretty much leave alone. The only use case for slider 5 with a low contrast object might be if you wanted to accentuate slightly the terminator. But again, as we were talking earlier, these large scale, slow wavelets, they can end up creating halos and create that kind of like limb banding sort of thing. So you want to, again, be very careful. So a low contrast object like UV Venus or maybe even Saturn, you may be playing more with slider 2, slider 3 than slider 3, slider 4. So looking at the interface for RegiStax, we have the Gaussian interface, the Gaussian controls here. But we also have a default view. Okay, and if we click default, notice that we no longer have the ability to key in sharpening or denoise. Those are gone away. You just basically have the slider at the various layers. So when we're using default wavelets, you're going to get a sharper, more aggressive, more edge enhancing outcome. The Gaussian wavelets, they are smoother, softer, and more noise controlled. So you get more granular control with your Gaussian interface as opposed to the default interface. The default filter is going to use a set of wavelet kernels that have a fixed sharpening profile, a fixed denoising profile, and a fixed response curve for each layer. So again, that's why you're not able to play with a lot of that. And these kernels that are used in the default, they were designed by the original RegiStax developers to be aggressive, high contrast edge enhancers. So that makes them ideal for high contrast objects like the moon, probably the sun, although I could see the sun benefiting from broader scale changes, and Jupiter for certain. So if you're going to choose the default wave filter, your target has to have strong natural contrast. Jupiter with its belts and zones, the lunar, obviously very high contrast object. Mars, especially when it is probably closer to opposition and a little bit larger, showing clear albedo boundaries, that's another good high contrast object. And basically, default wavelets do a great job of amplifying those edges. Another use case scenario is if your data has high signal to noise ratio. So you've got a good run under good seeing. The aggressive default kernel won't blow up the noise because you don't have as much noise. You had a good run. And so it can be very good in terms of pushing out some of those more subtle features that you've been able to acquire in your good imaging run. And of course, because it is more aggressive, it can generate halos easier, as well as if you push it too hard, you're going to get a less natural appearing result. So again, this is kind of like you understand a little bit of the science behind it, but there's still a bit of the art in terms of how hard you're going to push those layers in default or in the Gaussian interface. So we've been talking about wavelets. I thought it would be good to just take a moment and talk about deconvolution. So wavelets are boosting existing detail, but deconvolution is actually striving to recover detail that was blurred away. What deconvolution can do well, it can recover fine detail lost to seeing, It can sharpen the edges without boosting the noise aggressively. It can work well on lunar, solar, and planetary stacks. And if you had a night of good run, it can also restore sub-pixel detail if the signal to noise ratio was good. What deconvolution cannot do, it's not going to work well on noisy data. It cannot fix bad seeing. If your seeing was bad, there's not a lot you can do. And it is not going to fix if you have your collimation off. It cannot fix the undersampling issue. So another point is, and I think this is an important one, is that if you are going to go about doing some deconvolution, like for example, on AstroSurface or another tool that you like, which provides for deconvolution, you want to tackle that deconvolution first, because you don't want to do the wavelets, which will increase your noise in general. You're going to try to manage that, but you want to do the deconvolution so that you're not dealing with enhanced noise. And then after that, you go ahead and work your wavelets with it. Deconvolution, by the way, a lot of times it's SPF single point function, I think is what it is. If you were to look in LuckyStack Worker, there is deconvolution and the wavelets part. And the deconvolution, you can either have an artificial star, or you can actually go ahead and take a video of a star nearby your target and use that in LuckyStack Worker as a guide. So the star that you image kind of helps provide LuckyStack Worker with an idea of how to go about with the deconvolution to recover the lost detail. So, okay, wrapping up some of the key points. Your wavelets are basically multi-scale tools. Each slider is going to target a different size of details. In general, layers 3 and 4 tend to be the workhorses, especially for your higher contrast objects. Layers 2 to 3 for your lower contrast objects. Layers 1 and 6, you should probably avoid, or if you're going to use them, very light touch. Sharpening, when you are using it in the Gaussian mode, you're going to basically boost the strength of that layer when you are increasing the sharpening. You definitely want to suppress noise when your signal noise ratio isn't great. Fine layers are going to need more of that suppressing of noise, the denoise part. The default mode, you may want to try going, if you have a high contrast target, you may want to start off seeing how it looks with the default mode. And if you feel that you're not, getting where you want to go with it, switch over to the Gaussian filter and see if you can get get a better result by using that where you have more control. So the workflow, you want to get the filter right. Pick which filter you think is going to do the best job, Gaussian or default. You want to build your detail from the middle out. So you want to start around layer 3, move on to layer 4 or layer 2, and then decide if other layers, by tweaking and adding, twiddling with the slider, if that's improving the result. And again, I know I sound like a broken record at this point, leave layers 1 and 6 mostly alone. And then you want to make sure that you don't ignore the denoise. Mainly in the lower layers, add just enough to try to hide any visible noise that appears when you are evaluating where you've moved. You move the slider, you let go, you see the result. You want to try to back out any noise that has been introduced as you have moved the slider up to the right. And again, you can use those sharpening coefficients if needed. That's especially going to probably be indicated in a drizzled stack, or if you have soft seeing, low contrast object, Saturn, Venus. And again, a little counterintuitive, but a really good ROM with good signal to noise ratio, you can take advantage of the sharpening coefficients there to really draw out the full amount of detail that you have from that nice ROM. So that's pretty much what I had to say about wavelets. I appreciate everybody attending. You will get a follow-up email, and it's a brief survey. It's only like about 8 questions, shouldn't take you more than 90 seconds perhaps to fill out. So please take a moment and respond to that when you get that in your email. The webinar, as you know, has been recorded, and so it will be posted to our ALPO YouTube channel in the near future. Subscribe to the channel so that you know when new content is being made available. You'll be able to get a email or a ding to know that something has dropped. And so let's open it up now for any follow-up questions or comments before we wrap this up.
Yeah, I have a question, Jim. Can you explain undersampling and oversampling again? I don't quite. How do I know if my image is undersampled or oversampled? I never really understood that.
Right. So undersampling is where let's say you have a camera with large pixels, okay?
Yeah,
And inside that pixel, you end up having um, more detail. So in other words, it's like maybe the pixel actually spans the entire festoon. So you're going to kind of lose that festoon. Whereas if you had a smaller pixel size, it would pick up like right before the festoon, and then right after the festoon. But if you've got a large pixel, it's all mashed together. And you know, a pixel is a pixel. You can't discriminate and get detail out of that. So
right.
if you don't, basically, it's like if you don't have enough magnification, then you're going to get into undersampling. Um, I should have it in the top of my head, and I don't. There is a particular formula where you take the pixel size in micrometers, the pixel size of your camera, and I think you apply five as a value, the number five for average seeing, and that gives you the focal ratio that you should be achieving. So I know, for example, I have a 10-inch f6 Newtonian. So
Yeah,
for me, I need to be hitting somewhere around f20, f22, somewhere around in there to not be oversampling or undersampling. And of course, oversampling is the opposite. It's where you've got so many pixels that you're actually
yeah,
going to end up introducing noise, because it's too fine. So you want to try to hit that sweet spot where you're not undersampling and yet you're not grossly oversampling. What
yeah.
I will do, Greg, I'll find that a link to that discussion about how to get to the point where you're sampling properly.
Yeah, check the chat. Kevin put in pixel 2.9 microns times 5 is f50. That's what I use, 2.9 micron pixels. I find it good. I have a 10-inch Meet LX 200 GPS. So, yeah, I'm usually at f15, and I like using a
That's
even lower 1.25x Barlow. Yeah, to 1.5. I find 2x is too large. People use 3x too. But
yeah,
yeah,
yeah. But I mean, that particular formula that Kevin, thank you, Kevin, probably dropped into the chat.
yeah,
That is kind of like your guideline. That is kind of the target where you should be shooting for. So that's
right,
taking
right,
full advantage of the optics of your system and your camera. It's kind of pairing them up so that you're getting the ideal sampling.
right. I even bought I bought a ZWO camera that has 1.45 micron pixels, so I wouldn't have to use a Barlow. And I find the resolution is worse with that. I've tried both. I've tried like Mars, especially since it's small. I tried it with the 1.45 micron pixels, then 2.9 using a 1.25 or 1.5x Barlow. And the 2.9 with the Barlow images look better than no Barlow with the 1.45. I don't know why, you know, but either way,
Yeah, I'd have to,
2.9 I think is a really good pixel size to shoot for, yeah, to use.
yeah. And again, it's not just the pixel size, it's the native or the effective focal length of your imaging system of your scope
Yeah.
too. They both work together. So
All right.
good
Thank you.
question. Anyone have anything else?
James,
I wait.
uh, excellent talk. You really cleared up some things for me that I really didn't understand. I really have one comment though. You mentioned one thing you didn't mention. Uh, in the process of applying the wavelengths, it's possible to drive the image into saturation. So you need to keep an eye on that.
Okay, you broke up a little bit, Wayne. Can you say one more time for us? So I heard that something about the saturation.
Yeah. What it's saying was that in the process of applying the wavelets, if you drive them too hard with a highly exposed image, you can drive parts of the image into saturation,
Right.
and that then loses detail.
Yeah.
It's something you
No,
have to
good.
keep an eye out for. And if I remember right, RegiStax can show you the histogram as you're doing it,
It does. Yes,
let you
it
know when
does.
when that's happening.
Yeah. No, good point. I didn't cover that. Thank you. All right, folks. Anyone have anything else they'd like to address? All right. If not, I'm going to stop the, oops, try to stop the recording.